Let's work on a simple problem. Suppose we had 50 grams of ice that's at negative 10 degrees Celsius, and we dropped it into a beaker containing 50 grams of water that's at 80 degrees Celsius. After the ice melts, and assuming no heat is lost to the environment, what would be the final temperature of the system? So 50 grams of ice is at negative 10 degrees Celsius, and we dropped it into a beaker containing 500 grams of water that's at 80 degrees Celsius. After the ice melts, and assuming no heat is lost to the environment, what will be the final temperature of the system after it settles? So a few constants: Cp of water, specific heat, Cp of ice, we will use 2.06 for this problem, and heat of fusion for water is 334 joules per gram. So our main equation that we will be looking at is that the heat gained will equal negative heat lost. In this example, or heat, so heat always flows from hot to cold. So our heat, what's going to be gaining heat will be our ice, or 50 grams of ice. And what's going to be losing heat will be our 500 grams of water. I like drawing this diagram. On one side, we have negative 10 degrees Celsius ice. At the other side, we have 80 degrees Celsius water. When we mix the two, the ice is going to heat up and try to reach some final temperature. The water is going to cool off until it also reaches the same temperature. At the end, they'll both meet at the same temperature. The ice starts out as a solid. It's going to eventually reach some temperature, the melting point. Melting point of water is 0 degrees Celsius, at which point it will melt. And we have to make a guess. So we're going to guess that the final temperature is going to be in the liquid phase. So this piece of liquid keep it solid. We'll guess that the ice is going to melt and become a liquid, and that the 80 degrees Celsius water is going to lose some temperature and stay a liquid. This is a pure guess, but basically we use common sense. If you put some ice in some really hot water, you put a very little amount of ice into a lot of water, you would expect the ice to melt and the water to cool off. Final temperature. Because this is a subscript. Our main value is T, so that's temperature, and subscripts describe the variable. Like, for example, this is lost heat. This is a subscript, lost heat. This is gained heat. You read subscripts first, unless it's like a number like V1 and V2. Or we still say it TF, but the words is final temperature. So an example of where this guess would be wrong. Imagine you're in Antarctica and you have a giant big glacier. The glacier is at negative 200 degrees Fahrenheit, and you pour some hot water onto the glacier. In this case, we would expect the water to freeze and the glacier not to melt, right? So you basically have to guess here, and once you do all the math, it's basically common sense where this line is. But note that sometimes it could be down here, and the only times it'd really be down here is if you're pouring hot water on a giant big iceberg. Most of the time, the water isn't going to freeze, or instead the ice is going to melt. So we'd guess that the final temperature is going to be somewhere in the liquid portion. So let's analyze. So let's look at the gains heat side. The gain heat is going to be the 50-gram ice cube. What all heat does it? Let's calculate the total heat it gains. So looking at this diagram, we're seeing that it's going to have to go from negative 10 to 0 degrees Celsius. So the ice is going to heat up from negative 10 degrees Celsius ice to 0 degrees Celsius ice. The equation for this would be the change in temperature, the one that deals with change in temperature. Heat is equal to mass times change in temperature times specific heat. So that would be 50 grams. Temperature difference would be 0 minus a negative 10, which would be, and then times specific heat of ice is 2.06 joules per gram degrees Celsius. So 0 minus negative 10 will be a positive 10. 10 times 50 is 500. 500 times 2.02 is 1030. So this is from negative 10 degrees Celsius ice to 0 degrees Celsius ice. We also have, when it melts, it's going to gain some heat. It's going to go from 0 degrees Celsius ice to 0 degrees Celsius water. So this would be when it's melting. We use this version of the equation, mass times heat of fusion. So 50 grams is all going to melt. all 50 grams is going to melt. We're going to assume that. Note that in some cases, not all the ice will melt, in which case, we're not going to cover that example in class, but sometimes we don't know how much of the mass actually melts. It could be that, again, we guess here that it's going to be somewhere between 0 and 80, the final temperature. It could be exactly at 0, in which case not all the ice will melt. That's a special case, but we're going to guess that it's somewhere between 0 and 80, so all 50 grams melts. So we plug that all 50 into the equation, and we get 16,700 joules. The ice cube is now a liquid cube. It is melted. It is now at 0 degrees Celsius water, and it's going to increase up to some final temperature, still being water. We don't know what this final temperature is, but that will eventually solve for it. We will use change in temperature, mass times delta T times specific heat. The mass is 50 grams. Change in temperature is final minus initial temperatures. So final minus initial was 0. And we're in the water phase, so we use 4.18 for joules per gram degree Celsius as CP. We can simplify this. So anything minus 0 is that. So 50 grams times TF times 4.184 joules per gram degree Celsius. These are all being multiplied together, which means we can multiply in any order. So 50 times 4.184, the grams will cancel out, giving us 209.2 joules per degree Celsius times TF. And we've reached our final temperature on the left side. Let's now go back up to the left side. What loses heat? Well, that would be the 500 grams of water. The 500 grams of water starts out at 80 degrees Celsius water, and it goes to some final temperature and stays water. Again, we made the assumption that it's supposed to stay water. This is a change in temperature, so we use the change in temperature heat equation. The mass in this case is 500 grams. Change in temperature is final temperature minus initial temperature. So final temperature, or initial, is 80. And we're in the water phase, so it's 4.184 joules per gram degree Celsius. We can now do some simplification. We can FOIL this. 500 times TF. I'm going to drop the units right now. Simplify this. It's a hassle to keep units on while doing this simplification. So 500 times TF is 500 TF. 500 times minus 80 is going to be minus 40,000. So we simplify 500 times TF minus 80. We still have the 4.184 multiplied to it. And we FOIL this. 4.184 times 500 TF. That's 2,092 TF. And 4.184 times minus 40,000 be minus 167,360 joules. And this is going to be our Q loss side. So we have our gains and we have our losses. To get our final equation, we add up all of our, so again, starting out with our equation, Q gained is equal to minus Q lost. So looking at our Q gained, we have 1,030 joules plus 16,700 joules plus 209.2 joules per degree Celsius times TF, and that'd be equal to negative Q lost, and Q lost was 2,092. This would technically have been joules per degree Celsius, and then put units on them, minus 167,360 joules. So let's simplify. We can add these two together. That is 17,738 joules plus 209.2 joules per Celsius times TF. We can distribute this minus, like minus 1 or negative 1. Negative 1 times this, which is negative 2,092 joules per degree Celsius times TF. And we distribute this minus over here. Minus and a minus becomes a plus. All right. Now we have our final equation, and we just need to solve for final temperature. We have two final temperatures. We need to combine them to one side and everything else the other. So to get rid of minus 2092 TF on this side, I'm going to add it to both sides. Add it to and it'll probably be better for you guys just to leave units off while you're working. I like keeping them in to make sure I didn't make a mistake anywhere. So minus and a plus of the same number cancel each other out. We need to get rid of this term on this side because we want TF by itself. So minus 17,738 joules from both sides. And if you notice, I'm lining up the TF so that when you just directly counter them out, 17,000 minus 17,000 zeros, we can cancel that out, and we can work this out. So 209.2 plus 2,092. That would be 2,301.2 joules per degree Celsius times TF. And 167,360 minus 17,738 is equal to 149,622 joules. Now we take this and divide it on both sides. Again, just algebra. This divided by itself is 1. 1 times TF is just TF, so this cancels. And so we have TF, a joule divided by a joule, cancels, and we're left with degrees Celsius. And so I get a final temperature of 65.01912 degrees Celsius. This is one way of doing it by breaking it out. Some people are more visual learners and like to break things out and do one step at a time. Go ahead and simplify this version, simplify this, simplify this, simplify this. Then combine it and then do the algebra. Personally, what I do is coming back to my original problem. This is how I personally work it out. I do all my algebra all at once. Somewhat how I do it. I actually don't use numbers until the very end. So we start out with Q gained equals negative Q lost. And I know that I'm going to go from negative 10 degrees Celsius to 0 degrees Celsius. This would be for the ice. So I would plug in 50 grams. This is a change of temperature of 10 degrees Celsius. For ice, I'd use 2.06 joules per gram degree Celsius. Ice is then going to melt, so ice melting. I would then use the heat of fusion, M times HF, so 50 grams times heat of fusion. And then I'm going to add in it going from 0 degrees Celsius water to some final temperature. So that would be 50 grams times TF minus 0 degrees Celsius, 4.184 joules per gram degree Celsius. And that will equal negative. For the Q loss side, we're going down, and it would be 500 grams times change in temperature would be final minus 80 degrees Celsius. And it's in the water, so 184 joules per gram degree Celsius. And I work with the entire equation all at once. If you simplify all these down, all of this will turn out to be your 1030 joules. This is going to be your 16,700 joules. This is going to simplify down to this 209.2 times TF, leaving off the variable. That'll be equal to, simplify this down, all of this is equal to 2092 TF minus 167. And these would all be added. So you can either come up with one very large equation, or you can try breaking it up and trying to be neat. I personally work with one really big equation, mostly because whenever I look at this, I set my equation up and then I double check to see if there's a mistake. and then I work on the algebra. I usually don't make that many mistakes in my algebra if I start on it all at once. So I come over here, is this equation, is it set up right? Yes, it is. I'll continue working it on and do everything all at once. And you can add some labeling up above it. It's up to you whether or not you want to break it all out. It's literally the same thing. It's just that this is boxed off to show all the work here. I personally can do most of all this in my head, or not in my head, and with a calculator all at once. And it'll be this times that, this times that, times this, and then write it out. Doing the same thing here, negative 500 times this times TF is this. Negative 500 times this is this. And for me, it's easier to do this, but you can't really come back and see your mistake if you make one. And you can continue furthering, simplifying this down. And this would be 17,738 joules. And solve for it using algebra. Would say this is also 80 degrees Celsius. TF. Any questions? Yes, it's a lot of math, but this is all normal algebra that y'all should have covered. I highly recommend don't put units on it. The units are going to easily mess you up, especially if you're very messy on your units. For example, here I was kind of making my J kind of like this. That could be a 7, that could be a T. That could easily confuse me. Just know that Q is in joules. Temperature is going to be in degrees Celsius. That's really all you need to know. Just know that and your mass is in grams. And your CP is in joules per gram degrees Celsius. If your heat is in joules, your mass is in grams, and your temperature is in degrees Celsius, you know when you solve for TF, TF is going to be in degrees Celsius. Specific heat. Well, if there's no other questions, I think that covers everything. There's the keyword. Tomorrow we're going to go out. Do y'all think y'all can do all that math in 2-3 minutes? Probably not. The reason why I say that is because tomorrow we're going to have a lab. I'd like us to actually do that. I'd like us to predict before the ice melts what the final temperature is going to be. What's the best way of measuring the mass of the water and the mass of the ice? What method would you use? So we have a digital scale. And again, in real life and laboratory conditions, we actually have heat being lost in the environment. You leave boiling water on the counter, it'll just warm up. So to figure out the mass of water and the mass of the ice, so we can't wait long. Because if obviously we have a deal of water just sitting there, it's going to eventually cool off the room temperature. Some of the heat is going to be lost. So we need to be quick. We can assume that the ice is going to start melting immediately, that it's going to warm up to 0 degrees Celsius, which means we can remove this portion. But what we'll do is build a calorimeter, a coffee one, have it on a scale. We'll take the mass of cup. We'll then pour on water and we'll measure the mass of cup plus water. And we'll also take temperature to get a temperature. So I'll call this M1, this M2, and then we'll quickly add some ice. We can assume the ice is at 0 degrees. And then take the mass of cup plus water plus ice. And then close the lid. I'm going to call this M3. Foam lid will be better, but putting a plastic lid on is better than nothing. So the mass of water is just M2 minus M1, and mass of ice will just be M3 minus M2. And I have tested out to some degree the new digital thermometer, and it looks pretty good. What I might do is just write an Excel program and solve it. You just type it into the computer. So that's it for today.